Okay, hi, I'm Tom Bratton. Today I'd like to share some thoughts on hydraulic fracturing based on Wellbore images and geomechanics. In this presentation, I will highlight shear deformation in hydraulic fracturing geomechanics. What these data suggest about improvements over currently accepted practices is significant, so I'd like to give you some new things to think about. I'll present a hydraulic fracturing example using time-lapse Wellbore images, and along the way, I hope to illustrate how I solve what I consider a complex problem. I will define the characteristics of complex problems and highlight some techniques to solve them. I read a book called The Checklist Manifesto, How to Get Things Right. It was written by a surgeon, Atul Gawande, in 2009, and I found it a very interesting book. He talked about three kinds of problems. A simple problem, which he used as an example of baking a cake. He introduced complicated problems and complex problems. But the simple problem, his example was baking a cake from a mix. You go to the store, you buy the mix, you pour it into a bowl, add some milk and an egg, and turn on the oven, and the recipe exists, the directions exist, and there's a high likelihood of success. Anyone can do. His example for what he classified as a complicated problem was going to the moon. It can sometimes be reduced into a series of simple problems, but there's no straightforward recipe. Success in going to the moon required many people, teams in fact, specialized expertise. There were unanticipated difficulties that were frequent. Timing and coordination were always serious concerns. But what he said was, once you've done it once or twice or three times, the process can be repeated and can be repeated, quite well. His complex problem, his example was raising a child. Every child is unique. I can attest to that. These are my two boys. Michael is on the left and Jeremy is on the right. I think we were climbing Mount Sherman. I should have named the boys night and day because that's how different they are. Experience and expertise in child psychology, it doesn't guarantee success. In fact, the second child requires an entirely different approach. And because of that, success remains uncertain. So when I was reading this, I was thinking in terms of the oil business, and I thought, well, conventional reservoirs, there's few variables. We fairly well understand the physics and the modeling. And this is where Gawande said that workflows and checklists are adequate, and they're very helpful. You do this first, you do this second, and you do this third. Complex problems, on the other hand, I was thinking, yeah, this is a lot like the unconventional reservoirs, where we have many variables. We don't often understand totally the physics. I find if geomechanics is equivalent to predicting behavior, that certainly time lapse is required. I'd like to see how the formation behaves, and that's going to help me make a better prediction. Certainly more disciplines are required, and Gawande said, workflows and checklists are important, but they're inadequate. They won't get you all the way home. So I think a good example for a complicated problem is like bridge construction. This is the Tacoma Narrows Bridge, and I think many engineering students have probably studied this. They had built the bridge in I think the 1930s or so, and the first time the wind got up to I think it was around 40 miles an hour, the bridge started oscillating, and eventually it failed, and the bridge collapsed into the water. The color picture that you see here is the replacement bridge that was constructed after the first one collapsed. And when I think about that and think about geomechanics in the oil business, whether we're talking about the drilling domain or completions, predicting how a formation is going to behave when we drill through it or when we frac it is complex. And so to solve complex problems, I think time lapse is real interesting. There's one of the first time lapse images that I remember. This was published by Jean Desroches, one of my colleagues. We go into the hole with a MDT tool with a dual packer module. The packers are shown in green right here, and we'd isolate an interval and pump into the interval and frac the formation. And then we'd pull the tool and run the image again. And you can see clearly the creation of the induced hydraulic fracture. And everything looks fairly simple and normal for what you might expect. Well, today I'm going to give you another example of hydraulic fracturing. This is not in an unconventional reservoir. It's in a tight gas sandstone, actually. And the Wellbore images were acquired in open hole. An open hole packer was set just above the pay zone, and the formation was hydraulically fractured with a mini frac. And the packer was removed, and the Wellbore images were acquired then after this calibration fracture test. So I'll show you the log presentation. We'll look at this in detail. Tracks 1 and 2 are the static and dynamic image acquired after drilling. And so it's your typical at wireline time when you typically run wireline logs. Tracks 3 and 4 are the static and dynamic image of after the wellbore has been pressurized and hydraulically fractured. So we're going to take a look at this data. I'm going to look at it in segments. The entire interval is about 80 foot thick. The segment here is about 12 foot. Here is the tracks 1 and 2, the image after drilling, before stimulation, and 3 and 4 is after the stimulation. Each of these dark lines that you see, this is 1 foot. So again, this is about 12 foot. And you can clearly see that there's been some change in the image. You've got this classical, I would call it, hydraulic fracture that you see. It is interesting down here. There seems to be like a third hydraulic fracture, which is kind of hard to explain initially. If we scroll down and look a little bit deeper, this really surprised me when I saw this. What appears here appears to be like breakouts. And there's a lot of damage on all 4 sides of the borehole. When you compare to before, in fact, you look at this lighter colored layer, it's about 3 foot thick. It doesn't even have a fracture in it. It's got some breakouts. But there's no continuous hydraulic fracture going through that thin layer. So clearly, something needs to be explained. And then as we get down here, we just see a maze of fractures. Moving further down, we see more of the same. There's a split. It seems like the fracture turns into two forks on this side of the hole, but on the other side of the hole, it doesn't. And finally, at the bottom of the image, we see all this high angle fractures that are like on echelon. So, the first thing, you would say is how do we explain all of that? Well, another paper that I read that was actually published in Petrophysics quite some time ago by David Herrick, he looked at different ways we solve problems, and it all revolved in his mind around the data that you had and a mathematical model that might help explain the data. And of course, we recognize that if we have data and we have a model that he called it the scientific method, where the goal is insight and understanding into the behavior in this case, or into the mechanisms. The decisions you took would be based on that understanding, and the result was accurate predictions, which from a geomechanics point of view, that's where we're trying to go. But there's other ways there's other methods that people use, and he called, when you have data without a model, he called it the empirical method. And that's often employed in solving scientific problems. But this one really hit home, model without data. So this is like hydraulic fracturing before we had any kind of fracture diagnostic, such as microseismic data. And he called this the religious method because the goal is a believable model. And this is back in the time when we thought that you had two wings to every hydraulic fracture, and they were equal in length, centered about the borehole. And so I think to solve complex problems, we want to talk about data, which we've seen now, and a model. So I'd like to kind of introduce some basic geomechanics modeling to you and see how this model can explain what we observe in this very complex behavior. There's two kinds of failure that we commonly see. One is shear failure, which we use more Coulomb often to describe that. We have two differential stresses, or two stresses. The big one, sigma 1, is the largest, and sigma 3 is the smallest. And whenever those two stresses are greatly different, then the formation fails along conjugate shear planes, and they're typically about 30 degrees from the maximum stress. And of course, this is what causes faults in the earth or natural fractures. It doesn't always have to be 30 degrees. In fact, it's a function of the friction angle of the material. And this is one common type of failure. Hydraulic fracturing is thought to be tensile failure, where anytime your minimum stress becomes tensile, then you'll fail perpendicular to that stress. And that governs hydraulic fracturing. At least that's what we thought. The other component is, of course, the stresses in relationship to the strength. So at the far field, we have the vertical stress due to the overburden, and you have two perpendicular stresses that are in the horizontal plane. Usually they're different, and when they are, the minimum is called the minimum horizontal stress, and the larger of the two is the maximum horizontal stress. So I use small h and big H to denote that. But at the Wellbore wall, on the interface between the mud and the formation, you have cylindrical coordinates. You have a radial stress, which is due to the pressure of the mud. You have the axial load which is compressing the grains in the vertical direction. So it's very close in magnitude to your overburden. And then you have this hoop stress, which is generally compressive, and it acts parallel to the circumference of the borehole. So whenever we take a look at how do these stresses vary in magnitude and direction, I'm going to plot the stresses on the y-axis as a function of distance into the formation. And so 0 would be at the interface between the mud and the formation. And you get far enough away, and you could talk about these three stresses as being the far field, the vertical and the two horizontal. But if your wellbore pressure is low, then your effective radial stress, which I denote with a prime, is low. And the lower the radial stress goes, the higher the hoop stress goes, or the tangential stress. And like I said, the axial stress shown here in orange is very similar to the vertical stress. But there is a kind of a Poisson effect that varies with distance into the formation. To hydraulically fracture a formation, we raise the pressure in the wellbore to a very high number, up here, say, above 7,000 psi in this example, and it causes the hoop stress, or the tangential stress, to go negative or tensile, and causing a tensile failure at the borehole wall. I like to look at the same information in what I call a Wellbore stress plot, where I'm plotting these three stresses now as a function of wellbore pressure, or ECD, the equivalent circulating density. I originally did this work for drillers, and they tend to think in terms of mud density. But ECD is more than just the density of the mud. It includes the pressures of the pipe rotation and moving the pipe up and down, and the mud pumps going on and off. But anyway, the x-axis is just simply low wellbore pressure is here on the left, and high wellbore pressure is on the right. So the tangential stress is shown here in red, the radial stress in blue, and the axial stress is shown in gray. Anything that's in yellow is compressive stresses, where we're pushing the grains of sand together. Pulling them apart is shown in gray, or we use negative numbers for tensile stresses. And what we know from elastic theory is there's a one-to-one relationship. So every psi that I increase in wellbore pressure, I lose 1 psi in the tangential stress. And if I get my wellbore pressure high enough, I can force that tangential stress to go negative, to go tensile, and create the hydraulic fracture. What's interesting, though, is when you talk about shear failure, and keeping in mind that you always fail at a small angle to the big stress, that these dotted lines here are what I call mode transition pressures, which the geometry of the failure will change. So if you're going to fail at a small angle to the big stress, here, that's the tangential direction. Whereas if you fail at a small angle here, the maximum stress is not tangential anymore, it's axial. So you fail at a small angle to the overburden. So I'm going to use this and this model to explain the typical things that we see. Certainly a very common one is breakouts. It occurs in this range where the tangential stress is the highest and the radial stress is the least. This is a map view of a vertical wellbore, and so your hoop stress, or your tangential stress, is sigma 1. Your radial stress is the minimum, and it's perpendicular, and you develop these conjugate shear planes. And this little piece of rock right here, which looks like this, here's your surface created by the drill bit, and here's one conjugate plane, here's the other one. And this caving falls into the wellbore, gets filled with mud, and so your wellbore image shows this blurry, dark color, which is a mud-filled cavity because this material has failed and fallen into the wellbore. You get the breakout on the other side of the borehole. So half of it is here, and the other half is over here. This failure is aligned with the minimum horizontal stress, and it often gives rise to one caliper reading at or just less than bit size, which is the caliper reading on this side of the borehole. And the other caliper, the orthogonal caliper, reads larger because that caliper arm is in this cavity. So that's a typical breakout. I can have failure in a different geometry. I call this a shallow knockout. And what happens now is the axial load is now the maximum stress. So shown in the diagram, sigma 1 is here, your radial stress is the minimum, and so your conjugate shear plane is in this geometry with respect to the borehole. This failure is also aligned in the minimum horizontal stress direction, and it gives rise to a caliper that goes back and forth, which is typically bad hole that we see in weak shales. And in the image, it might look like a narrow breakout, but it's often a narrower failure, and it's occurring in the same azimuth as the breakout, which occurred here. If we go into this regime, now the axial load is maximum, but the tangential is the minimum. And so sigma 1 is vertical, sigma 3 is tangential, and you end up with these on echelon cracks in the image. And you know that they're not natural fractures because they don't go all the way across the borehole. And in fact, you'll observe a lot of the symmetry is not there. You can't put a sine wave through this and go through the equivalent one. Very often you'll see them on one side of the hole and not the other. But this failure is aligned with the maximum horizontal stress. And the fourth mode of failure is what we think happens in hydraulic fracturing, where the wellbore pressure is so high, this tangential stress goes into tension, and we pull the rock apart, and we get this nice vertical tensile crack, which is the induced hydraulic fracture. So there is a model that goes along with the data. So I'd like to go through this image a second time and explain what I'm seeing in the image. The first thing I see is two rings of my tensile fracture. The aperture or the fracture width is really quite large compared to say down here where the aperture is less. It's a different kind of rock, but clearly this is what I would consider a formation that failed in tension. And in fact, you see a second crack that is leaving the borehole. The borehole is a vertical well, but they're not perfectly vertical. And so here's where this fracture left the borehole, and you can see the same thing here in the secondary tensile fracture. But we get down here, and I'm beginning to see a lot of conjugate shear planes. So I'm thinking this might be shear failure. If we go on down, then what I begin to see is here's a breakout, and we're getting a lot of damage in line with the breakout, both above the breakout and below. This is what I call the shallow knockout, and it's when the axial stress is the largest and the radial stress is the minimum. So there's a change in geometry at the bottom of this layer. You can also see that there's drilling-induced damage that was there from the drilling, and this angle right here shows you that it's shear. After the stimulation, it's kind of combined and almost looks like an open natural fracture going all the way across the wellbore, but we know it's not because we imaged the formation before we raised the wellbore pressure and did the stimulation. We get down here and we get a lot of damage in the direction of the maximum horizontal stress, and we see damage in the minimum horizontal stress direction. So I think I can explain what we're seeing there. As we go down deeper, I'm seeing the same kind of behavior. I see some splitting that we have here, but overall, these apertures are quite a bit less than if it's induced in tension. And then finally, we get down to the bottom, and this formation down here is failing totally in shear. It's not failing in tension at all. And you can see that that's how it behaved due to the drilling stresses. And in fact, you see the same sort of thing up here, where you get these conjugate shear planes, which is all shear-induced failure. And it's not tensile failure. And so what this really tells me is, I'm seeing a lot of different failure modes observed in these images. Much of the failure is due to shear. It's not just tensile failure. There is some tensile failure, but there's a lot more shear failure in this example than what there is tensile failure. So the takeaway message is when a rock is stressed, it will fail in its weakest geometry. If the shear stress exceeds the shear strength prior to the tensile stress exceeding the tensile strength, the rock will fail in shear. Alternatively, if the tensile stresses exceed the tensile strength prior to the shear stresses exceeding the shear strength, the rock will fail in tension. So admittedly, shear stresses are important in the initiation of fractures. And when you're in a cylindrical environment, it's not the same as if you're in the far field. So you're in these cylindrical environments with borehole deformation, with perforations are circular, and you have to contend with wellbore stresses. But as you propagate away from the borehole or the perforation, shear failure is perhaps less likely in the far field. But when you consider these unconventional reservoirs are high on their stress strain curve, in other words, weaker formations are closer to failure than strong formations, and many of these unconventional reservoirs are already kind of fractured with either natural fractures or due to the digenesis and the maturation process of the kerogen. So many reservoirs are really in a state of confined failure, and there's faults and fractures that are observed. So much of what I think goes on in hydraulic fracturing is a lot of shear deformation as well as some tension. When you inject fracture fluid, you change the effective stresses, and that alters the picture as well. So you can see this. This is a nice paper published by Roberto Suarez Rivera at Terratech when he was there. This is a large scale test where, and it's a NIO outcrop rock, and they drilled a horizontal borehole through this and fractured it right here. So here's your vertical hydraulic fracture. The stress state was the intermediate stress was 2,500 psi applied to this face. Your minimum stress was on this face, and then the overburden loading was 3,500. And what surprised everybody was how much of the fracturing fluid penetrated along bedding planes. And that was totally unexpected from any of the fracture modeling that had been done at the time. And so we're beginning to see that these weaker materials often behave, deform in shear, and sometimes before they deform in tension. We've seen this as well, and this is a paper I published in the first break, where we looked at the Niobrara Formation here in the Denver Basin and compared the overburden stress with a defit or the minimum stress. And this stress differential is just very, very large, especially compared to the high clay that you see like in the Sharon Springs. And so if you're close to failure or at failure, I color code it red. If you're low on the stress strain curve, you're green. And if you've gone beyond yield, you're kind of in the yellow. So this work suggests that even at the far field, that formations are under a tremendous amount of shear stress, where the overburden or the vertical stress is 1.1 psi per foot, and your minimum horizontal stress by defit is somewhere down around 0.7. So in recap, there's a couple of things I'd like to mention. I think time-lapse image data was used here to really observe what happens to a formation when you pressurize the wellbore. We use geomechanical modeling as a key to explain the different failure geometries, and a comparison of the model with data. This is the hallmark of the scientific method and gives insight into understanding the mechanical behavior. So what were the insights? Well, the takeaway for me is hydraulic fracturing, especially in unconventional reservoirs. It exposes the formation to both shear and tensile forces. I mean, that's very clear. And many formations fail in shear prior to failing in tension. So, and we've seen that. We also see the apertures in shear fractures are much less than what we see in tensile fractures. This is one reason why I think we have screen outs, and why in unconventionals we go to smaller proppant sizes like 100 mesh. And the other final insight is, this provides a basis to ask additional questions like, why is it that hydraulic fracture simulators only consider tensile failure? And I think this is kind of a follow-on from the religious method, where we started hydraulic fracturing reservoirs in the 40s before we had any kind of modeling, and before we had any kind of data. And we did have our models, and so we trusted in those models. Another question is, leak-off interpretation. This is one of the ways we use to calibrate our mechanical earth model, but yet all leak-off interpretations I've seen only consider tensile failure. Here's a good example of a typical leak-off test. But I suggest an alternative interpretation. Point 1 here is where you see the initial slope deviating. I think this could be interpreted as where fluid begins to leak into the fracture due to, say, a high angle echelon fracture. You increase in pressure until you get into the far field, and then the test is terminated here, because drillers typically don't want to break down the formation. And then they shut in for a period of time, 10 minutes typically. But tensile failure mode is generally what's applied in interpreting this data. But alternatively, if it's a weak formation that fails in shear before it fails in tension, then you ought to be using more Coulomb as your failure model rather than your tensile strength failure model. And you'll come up with totally different calibration numbers for your mechanical earth model. So, in summary, let me finish with this. I'd like to convince you that shear deformation is important in hydraulic fracturing. It's especially important in unconventional reservoirs. It'll help in defining a better vertical stress profile because many formations don't behave according to linear elasticity. They're already in a state of confined failure. I think shear deformation is a good thing. I think it leads to much more surface area that can be exposed to production, which is why I think these unconventional reservoirs work. It gives much higher effective permeability because of all the shear deformation. And I think the solution to solving even more complex problems involving geomechanics and complex behavior, we need different kinds of data, time-lapse data. I think DAS cables are giving tremendous amount of insight into the deformation occurring during hydraulic fracturing. And I think we need to open up our minds to diagnosing which formations fail in shear and which ones are failing in tension. And the integration provided by new insight is going to give us a better prediction of the hydraulic behavior. So I'll conclude with that. I'd like to emphasize, I think integration is important. I define it as the synthesis or the bringing together of multi-scale time-lapse data, data acquired over time, multidisciplinary data to solve complex multivariate problems. I thank you for your time and your attention, and that concludes my talk. Thank you.